So today we'll finish up our discussion on EDFAs. So last time we had derived these propagation equations for the signal and idler powers. So for the pump and the signal wave powers. Right? So we had used some approximations, like the plane wave approximation, assuming that basically the intensity is constant inside the core. We don't take the mode profile explicitly. And the second approximation we made was the small signal approximation, basically assuming that the signal powers are small, right, compared to this intensity that we defined in terms of the atomic parameters. Right, so under these approximations we derive this equation. So for the pump, right, the equation is like that. So because you can see this is a minus sign, so the pump gets attenuated as it's propagating, right? And then the signal equation was like this, right? So then depending on this sign of this term here, right? So if this is positive, then you can see the signal will acquire gain. So let's look at the behavior in some limits, right? Again, to solve these exactly, these are nonlinear differential equations, right? So typically you will have to solve them mechanically. Analytical solutions in general won't exist. So, but in certain limits we can see what the behavior is. Right, so let's look at the initial like the initial small length along the fiber just after the input. So basically the pump hasn't depleted yet, right? So basically we are just looking at the first, let's say first meter or so after the input, right? So the pump hasn't decayed too much. So basically, so the input pump power, typically the pump power that we launch is, so last time we discussed that this PP naught was typically for the EDFA typical parameters was about a milliwatt. Okay, typically the launched pump powers are above that, so few milliwatts, tens of milliwatts, even hundreds of milliwatts. Okay, so basically the pump power we say is much bigger than this constant that we had defined. Okay, along for the initial part of the fiber when the pump hasn't decayed too much. Okay, so under this approximation, this equation, 1 over 1 plus P by PP naught, we neglect the 1, right? So PP is much bigger than PP naught. So you can see then, so we neglect the 1 here, then the P's get cancelled. And the equation that we get is this, okay? So now, so this is a constant on the right hand side, right? All these numbers are constants. So you can see that the pump power as a function of length in the initial part of the fiber is just decaying linearly, right? So we just integrate, we'll just get right? So PP at 0 is the input pump power that is launched, right? So this is the input pump power. And along the initial small part of the fiber, the pump is decaying linearly with length. Okay. So again, if you make this approximation in the equation for the signal, again, so we'll neglect the 1 compared to PP over PP naught here, and then also neglect the 1 compared to PP over PP naught here, right? So eta s, as we saw, is between 1 and 2. So we neglect these ones here. So then you can see that this factor of PP by PP naught gets cancelled in from the numerator and denominator. So for the signal, we are left with okay. So this equation. So this is dP by dz is some constant here, right? And sigma SA times eta s is just sigma SE, right? Because this eta factor was the emission cross section divided by the absorption cross section. So sigma SA times eta s is just like sigma SE. So again, this is a simple differential equation, right? So the solution is, you can see, it's an exponential gain, right? So we have dP by dz is some constant times P. Okay, so the signal is experiencing exponential gain with length in the initial part of the fiber, right? And the gain, you can see, is proportional to this emission cross section and the doping concentration of the erbium. Right? Makes sense? The higher the doping, the higher the gain. So that's the behavior along the initial part of the fiber. Right, now let's look at the other extreme. So towards the end of the fiber. Right, so after okay, so now the pump has decayed quite a bit. Okay, so basically the pump power has now become much smaller than this PP naught. Okay, so now we neglect PP over PP naught with respect to 1. Okay, because that becomes 1. So now the equation will become okay. So now you can see the pump will have exponential decay, right? So this is minus some constant times 1. So towards the end of the fiber, the pump is decaying exponentially. Okay, now if you look at the signal, right, so now again we neglect PP over PP naught with respect to 1. So in the numerator we just have -1, in the denominator we have 1. So right, so now you can see even the signal starts getting absorbed. Right, so because the pump has decayed to a very low level now, right? So it's not able to cause population inversion, right? So now you have more atoms in the ground state 1 compared to the excited state 2. So basically, that the signal also starts getting absorbed, right? So we don't, the condition for gain that this eta n2 minus n1 should be greater than 0, that is not satisfied. Right, so you can see here that we don't want a very long length of the fiber then, because after some point the signal also starts getting absorbed. Okay, so the signal power actually start going down. Right, so there's you can imagine now that there is an optimum length of the fiber. Right, so in the initial part the signal will start experiencing gain, the power will increase. Then at some point it will reach a maximum and then start decreasing. Okay, so for maximum gain we want a particular length of the fiber. Right, if you take longer lengths, then actually the signal power starts actually going down. Okay, so let's look graphically what these equations imply. Right, so if you look at the pump, the variation of the pump power as a function of fiber length. Okay, so x-axis is fiber length in meters, y-axis is pump power in milliwatt. Right, so depending on the initial pump power, right, so along the first part of the fiber, the pump decreases linearly with length, right? So let's say we start with 7 milliwatts at the input, initial decrease is linear, okay? And then eventually you start getting exponential decay. Okay, so the initial part is linear, and then here okay, so this is for an input of 7 milliwatt, right? We will start from 7. So the behavior looks similar for different input pump powers. You just start from the power level that you inject, right? But the behavior is sort of the same. So initially it decays linearly, and then there's an exponential decay towards the longer length. Okay, so you can imagine now, so for like here, the pump power is decayed down to very low values, right? So this PP naught that remember this was like around a milliwatt, right? So once the pump power decays to around a milliwatt or so, now, right, beyond this you start getting to this regime, right, where the pump power is not enough to cause population inversion, and the signal will also start getting depleted. So if you look at the signal, Okay, now we are plotting the signal power in microwatts. Okay, so the signal power is much lower than the pump power. And same fiber here. Okay, so the injected power, let's say, is 1 microwatt. Okay, so here basically at the input, the signal power is 1 microwatt. Okay, so now we can look at again these 3 different cases for input power: 7 milliwatt, 5 milliwatt, 3 milliwatt. So for 7 milliwatt, you can see the pump power is the highest. So the gain will be the highest. Okay, and again the behavior is initially you get exponential gain. So this is something like this. Okay, so this is for an input pump power of 7 milliwatt. Okay, so you can see that for 7 milliwatts, right, even at like a fiber length of around 7 meter, the pump power is still above this PP naught, right? It's still above 1 milliwatt here. So basically, we don't get to this regime, right? So for 7 milliwatts, it's sort of the signal power doesn't reach the regime of starting to fall down. Okay, we're still in the gain regime. For lower powers, pump powers, you can see that we'll start reaching this gain saturation regime where the signal will start. Okay, so here the signal starts like saturating, and so this is for 5 milliwatt. For 5 milliwatt, basically it just starts to reach PP naught around 6-7 meter length. And for 3 milliwatts, it's already below 1 milliwatt for like beyond 4-5 meters. Okay, so then for that, the signal actually starts falling down. Okay, so this is for 3 milliwatt. Okay, so you can see depending on the pump power, the optimum fiber length for maximum gain is different, right? So depending on the pump power that I use, I'll have to choose the fiber length appropriately. So for 3 milliwatts, basically the appropriate fiber length is around, let's say, 5 meters, right? And going longer than that actually reduces my signal power. Okay, so around 5 meters is the optimum length for 3 milliwatt. For 5 milliwatt, the optimum length is around, let's say, 7 meters. If you go beyond that, it will fall. Okay, so as you increase pump power, the optimum length is longer. Okay, so you can see that basically as we go along the fiber, right, the gain first sort of increases and then it saturates and starts falling down. Right? So if you plot sort of the gain, which is the output signal power divided by the input signal power. Okay, so this is gain dB, right? So which means this is like 10 log 10 of the signal power at the output divided by the signal power at the input. Right, so 10 dB gain means the output power is 10 times, 20 dB means the output power is 100 times, and 30 dB means the output power is 1000 times the input. So for different pump powers again, so again x-axis is fiber length. Okay, so this is again for 3 milliwatt, 5 milliwatt, 7 milliwatt. Right, so again for low pump powers, so 3 milliwatts, the gain reaches a maximum around let's say 5 between 4 and 5 meter length. Then it starts decreasing, right? As we increase the pump power, the point at which you reach maximum gain is now shifting towards longer lengths, right? So for 5 milliwatt, the peak gain occurs around 7 meters, right? And for 7 milliwatts, up to 7 meters, the gain is still increasing. Right? So basically from this, if you now plot the optimum fiber length that gives me maximum gain, right, as a function of input pump power. Okay, so it looks like that. So the optimum length of the fiber increases with input pump power, right? So yeah, so basically I have to choose the length of this erbium-doped fiber appropriately given what input pump power I'm using. If I use a longer length, so for 5 milliwatts, let's say it's about 7 meters. If I use a longer length, then actually the gain reduces. So we can also look at how the gain looks as a function of pump power. For different fiber lengths. So again, I'm plotting gain of the signal in dB versus now input pump power. Okay, so we can plot this for different fiber lengths. So for example, for a 3-meter fiber, it looks something like that. So you can see that the gain increases up to some level of pump power. After that, actually it saturates. Increasing pump power doesn't give me anything. Right, and that's because basically beyond this, beyond a certain length, the the pump power has already decayed, right? So increasing pump power doesn't give me much improvement. So now if we plot for right, so this is for 4-meter and 5-meter. Okay, so the saturation occurs at higher pump powers for longer lengths. Okay, so for longer lengths, I can go. The gain increases up to a higher amount of pump power, but beyond a certain pump power for any length, beyond a certain pump power, the gain sort of saturates. It doesn't increase any with pump power. Okay, so in summary, basically what's going on if you want to have one plot that summarizes basically what's going on in this EDFA or cycle. Okay, so let's look at how different quantities are varying along the length. Okay, so for example, if you look at the number of atoms in this ground state N1, right? Or maybe let's start with what we've already seen. So, for example, the pump power, right? So it first decays linearly and then it decays exponentially. Okay, so this is the variation of the pump power. So I'm plotting the pump power at distance z divided by the input pump power. Okay, so it's starting from 1 and then decay. Right, so this we've already seen. Now if we look at so the number of atoms in the excited state 2, right, N2. So we know basically that it's the pump which is causing the population inversion, right? Basically the pump is causing the atoms to go from 1 to 3 and they immediately decay to 2, right? So the higher the pump power, the larger the number of atoms in this second level, right? And if the number of atoms in the second level, so this eta n2 minus n1, if it's more than 1, then we get gain for the signal, right? So in the initial parts here, when the pump power is large, the number of atoms in 2 will be large, right? And we'll get gain. So if you plot the number of atoms in this excited state 2 as a function of length, so this looks like this. Okay, so this dotted line here is basically the number of atoms in the second level, right? Normalized to the doping level of the erbium, right? So you can see in the initial parts here, the fraction of atoms pumped to the second level is very high, right? So here, like it's almost 90% of the atoms are in 2, right? So up to a certain length, like a large fraction of the atoms are in the excited state when the pump power is high. Like equivalently, now we can plot n1. So again, n1 plus n2 is basically just n0, right? So that is distributed between 1 and 2. So 1 minus this will just be n1. So that looks like this. Right, so they'll cross at like 0.5 here. So this is n1 by n0. Right, so as the pump decays, it's not able to pump as many atoms to 2. So the number of atoms in the ground state 1 increases along the fiber length, right? And at some point, you can see at some length, n2 becomes equal to n1, and beyond that, actually now n1 becomes greater than n2. Okay, so you can now imagine in this regime here, now we don't have population inversion anymore, right? So there won't be gain. There will be gain only in this part, but not this part. Okay? So for example, now if you look at the signal power, so up to this point here, it will acquire gain. And then after this, it will start from. Okay, so this is signal power divided by input signal. Or not PL0, but the maximum signal, which reaches 1 at some particular length. Okay, so I hope that's clear, basically, right? So we launch some input pump power, it gets absorbed by the atoms, the erbium atoms, right? So because of this absorption, the pump power falls. Because of this absorption, basically atoms are getting to pump to level 2, right? So when the pump power is high, this number of atoms is in the level 2 is high, but as the pump power falls, this atoms in the excited state fall, and correspondingly the atoms in the ground state increase. At some point, you don't have population inversion anymore, right? And after that, the signal will start decay, right? So the gain will happen up to the point where you have population inversion. For a given length. You mean like this one, right? Yeah, so we saw that basically the pump is decaying, right? So you can imagine, so let's say, so you start with some pump power here, right? And then now you start with a higher pump power here. You start with a higher pump power here, right? So basically, right, so for a given fiber length, so this is the length, right? So beyond some point, basically the pump has decayed so much that the change in pump power is not giving you much any gain at all, right? Because they also, irrespective of where you start from, right, they sort of all decay. And you can see here, like for example, already for a certain, so what's happening here is that basically, so now for a given, so let's take some 5 meter length. So what's happening is that once you reach this power of, let's say, 5 milliwatts or something, this population inversion level is already like close to 100%. Okay? So at this pump power, already like you've inverted 100% of the atoms. Okay, at least for the initial part. Okay, and basically now if you increase pump power further, this can't go beyond 1, right? Basically, once you pumped all the atoms to 2, that's it, right? So basically, increasing pump power doesn't give me larger population inversion because I already have 100% population inversion, right? And the other fact is that basically because the pump is decaying, so after some point, the pump powers, the initial difference in pump powers goes away. So basically, both these factors sort of contribute to this saturation we are seeing here. Right. So of course, so this discussion we are doing in some limits, but to get this exact plot, you have to solve the exact differential equation, nonlinear differential equations, right? But physically, basically we can explain it this way. Right. So beyond a certain pump power, I don't get more population inversion. I already have 100% population inversion, right? And also, the pump powers decay after a point. They decay so fast that basically, irrespective of my input pump power, the final pump powers are sort of similar. Okay. Okay, so we can see a related effect here, which is called signal or gain saturation. Right. So here, I mean, we sort of saw it already. So another factor which contributes is so far sort of we talked about just the effect of the pump, right? But we made this small signal approximation, right? So we neglected actually the dependence of the signal power, right? We just said that it's small. But once it acquires enough gain, right? So here you are seeing like it can get 30 dB gain, so it can become like 1,000 times. Right. So once it starts acquiring large amount of gain, then basically it starts becoming close to this PS0 value, right? And we can't neglect it anymore actually. Okay. So that also contributes to this gain saturation because actually the equations we used, we neglected the signal, right? But there was also signal power in the original equations. There was also signal power coming, right? So another factor which is contributing, so basically if you look at this population difference here, the original expression was like this. Okay, so you can see there is signal intensity or signal power coming here in the denominator. Okay, and actually, so the equation for the signal intensity was like this. Right, so depending on the sign of this or the value of this thing, the amount of gain that the signal experiences depends on this population inversion value, right? But actually, so in the small signal approximation, we just neglected IS. But now once the signal acquires sufficient amount of gain, you can't neglect this IS anymore. And you can see that this population inversion actually goes down with increasing signal power, right? And why that is happening is actually right. So that once the signal power is becoming strong enough, then it's actually causing enough stimulated emission that it's pumping atoms back down from 2 to 1, right? So it's actually reducing the population energy level, right? And so you can see that as actually the signal power increases, the gain will go down because of this, right? So that's another reason for this gain saturation. So for example, so one thing is, so for example, if I plot the output signal power as a function of input signal power, okay? So if I have a constant gain, then I should just expect a straight line, right? So the output signal power divided by the input signal power is the gain. If I have a constant gain, then I should just expect a straight line. But what happens is that actually, as you increase the input signal power, the slope actually keeps going down, right? Because the gain value is actually going down with increasing pump power. Okay, so this is some kind of saturation you can see. This doesn't keep going up like this. And that's because, again, the gain value is inversely proportional to the signal power. Okay, so in terms of gain, if I see, so the gain now actually depends on the input signal power, right? So under the small signal approximation, basically it's independent of the input signal power, because we said that the signal power is very small compared to all other constants in our equation. So, but if you take this term into account, then actually the gain depends on the input pump power, right? So I plot gain right? And the gain is basically the slope of this curve. So for low powers, I have large gain, but as I increase the signal power, the slope goes down. Right? And actually this effect is also contributing to this saturation with the pump power that we talked about, because actually as you increase pump power, the signal power also increases initially fast, right? But as the signal power is now increased, it will cause a reduction in the gain. Okay. So as you increase pump power further, the signal power initially increases, but then actually that causes a reduction in gain. So that also contributes to the saturation with the pump power, increasing pump power. Right. So on the x-axis, I'm plotting input signal power. This is in dBm. Okay, so I'll have to define this dBm. Okay, so dBm is a unit for power. So basically, the power in dB. So since there's a dB here, we have 10 log 10 of the power in milliwatts. Okay. So basically, you normalize the power to 1 milliwatt and then take dB 10 log 10. Right. So, for example, 0 dBm is 1 milliwatt. Right. Minus 10 dBm is 100 microwatt, and so on. Right. So minus 30 dBm is 1 microwatt. So these dBm units are convenient, for example, when you're considering some link with a lot of losses, right? So you have a lot of losses in dB that you want to take into account. If you take the power in dBm, basically you can just add up the losses directly. You don't need to take exponential and log. Okay, right. So that's why they're convenient. But yeah, so basically the gain goes down, right? So looks like that. So these are for different. So this is for a pump 15 milliwatt. This is 10 milliwatt. 5 milliwatt. Okay. Yeah. So basically, once the input signal power is beyond a certain level, it's now strong enough that it's causing a reduction in the gain. So instead of the input pump power, sometimes this is also plotted in terms of the output. Input signal power is plotted in terms of the output signal power. Right, so that sort of gives me an idea of how much power I can get out of the amplifier. Right, so now I'm plotting the output pump power, or output signal power. Okay, so if you plot with respect to output pump power, it looks more sort of flatter here, and then it drops steeply. Okay, and we can define output saturation power by the point at which basically the gain drops by 3 dB. Okay, so we have some small signal gain here, right, for low powers, which is sort of constant until the power reaches some high value where it starts causing a reduction in the gain. So where the gain drops by 3 dB, right? So if you look at this power here, this is known as the saturation power. So that sort of, again, so these three curves are for the different pump powers. So 15 milliwatt, 10 milliwatt, 5 milliwatt. So this is sort of like a measure of how much power I can get out of the amplifier, right? How much signal power I can get out. Because if I want more signal power, actually the gain drops quite steeply. So actually the output power won't change much, even if I increase, for example, the input signal power. Right, and the saturation power that I can get out of the amplifier, that increases with increasing pump power, of course. Right, so typically the saturation power is some fraction of the input pump power. Okay, so for example, if you have pump power in the 10 milliwatt range, then the saturation power will be like a milliwatt or few milliwatts. That's the maximum power I can get out. signal. But you can have EDFAs with much higher pump power, up to watts, where the output signal power can be much higher, hundreds of milliwatts. Okay, so this final couple of things to discuss about the EDFA. So, if you look at the gain spectrum, right? So basically, for some applications, so like for example, if you have a WDM wavelength division multiplex system where we are sending multiple wavelength channels through the fiber, right? And the nice thing about the EDFA is that the gain bandwidth is broad enough, right? It covers like 1530 to almost 1600 nanometers. So we can amplify different wavelength channels within this range simultaneously. Okay. So if you plot the gain as a function of wavelength, okay, so x-axis is the signal wavelength in micron. Okay, and then we plot, so as we increase pump power, right, so recall all these were actually functions of frequency, right? So this depended on the emission and absorption cross section, which is actually a function of frequency of wavelength, right? So as we change pump power, we change N2 and N1, but that's a function of wavelength. Okay? So for different signal wavelengths, this value population inversion, hence the gain value will be different. Okay, so we define this parameter normalized pump power, which is the input pump power divided by this PP naught. Right, so this is basically the input pump power divided by the mode area at the pump, right? So this is, for example, if you use a Gaussian approximation, is the spot size at the pump by omega square, where omega is the spot size of the pump, or in the plane wave approximation, we just took this as the core size. And this PP naught was basically right. So gamma equal to 0 means no input pump power. So that's no pumping. So for that, actually, the gain is always less than 0, which means you only have loss because there is no pump, right? So all the atoms are in the ground state, so the signal will only experience loss. So as I now increase gamma or the pump power, basically this curve now starts shifting up. Okay, so for gamma equal to 1, we can see that now wavelengths beyond 1.55 microns start experiencing gain. Right, so now again longer wavelengths starts experiencing gain first because their emission cross section is higher compared to the absorption cross section. Right. So now we increase this further. Now more wavelengths start experiencing gain. Right, and at some point basically the entire so this is gamma equal to 2, gamma equal to 5, gamma equal to 20. Right, so for large input pump powers, which is why basically we operate EDFAs usually, the peak gain occurs at around 1.53 micron. Okay, but you can see that the gain is sort of flat over a broad region here. So we can simultaneously amplify multiple wavelengths in this region. Okay, so the spectral bandwidth here typically, if you take like a 3 dB gain bandwidth or something, this delta lambda is about 30 nanometer, around let's say 1.55 micron. So in terms of frequency, this corresponds to about 3.7 terahertz. Okay. So for example, now if you have a WDM grid, so usually the wavelengths are spaced at a particular spacing. Typically, so for example, for dense WDM systems, this is about 0.8 nanometer, the wavelength spacing of different channels. Right, so you can see that I can have like, for example, 40 wavelengths within this 30 nanometer. So I can simultaneously amplify 40 channels. And the last thing I just want to briefly mention is noise figure. So any amplifier always adds noise to the signal, right? It doesn't come for, this amplification doesn't come for free. So if you have any noise in the input signal, that also gets amplified, right? So the signal gets amplified, the noise also gets amplified, but actually it's much worse because the amplifier also adds its own noise. Okay, so basically what happens is that the signal to noise ratio actually becomes worse, right? So this noise figure is defined as the signal to noise ratio at the input divided by signal to noise ratio at the output. So the output signal to noise ratio is worse. So if this F is always more than 1. Okay, so for example, if you want to, so my input, let's say, so I have this WDM signal, right? So I have some different wavelengths here with some powers here, right? So now I send it through the amplifier. So what happens is, of course, these wavelengths get amplified, so the peak value increases, right? But also there's a background noise added. Okay, so the spectrum looks like this. There is some background noise here, which is known as amplified spontaneous emission noise. Right, so for the EDFA, the noise is coming from spontaneous emissions. Right, and the spontaneous emission occurs over this entire gain bandwidth. Right, of course, the stimulated emission is happening only where your signal is present, but the spontaneous emission is happening everywhere. Okay, and that gets amplified also. So it's called amplified spontaneous emission. Right, so if you have, this is the signal to noise ratio, right? So this is the signal level and the noise level is here. So this difference here is, so if this is in dB, then this difference here is the signal to noise ratio of the input, and here now you have signal to noise ratio of the output. Okay, so this would be smaller than this, although the peak level has increased, right? So typically for EDFAs, this depends on basically the population inversion level here. Okay, so it depends, the noise figure depends on N2 divided by N2 constant. Right? So you can see that F is always greater than equal to 2. Right, so the best case occurs when when N1 is 0. Right, all the atoms are in N2, in level 2, so then this is 2. But for any other case, if you have some fraction of atoms in level 1, so not perfect population inversion, then you can see that this will be greater than 2. Right? Or in dB, right, if you take the dB of this is always greater than 3 dB. So 3 dB is the best noise figure you can get. Okay? And yeah, typically this is the case for most amplifiers. And actually for EDFAs, one can reach this limit of 3 dB for large gain and high pump powers. Okay, so typically, for example, if you plot the noise figure here in dB versus input pump power, milliwatt. Right, so this 3 dB is sort of the best you can do. So typically, it starts from a high noise figure, but then for high pump powers, it sort of approaches this ideal limit. Okay, so actually EDFA noise performance is quite good. Like compared to if you take any electronic amplifiers or something, they will typically have much higher noise figure value. But for EDFAs, you can see that you can get close to this 3 dB limit for large pump.